Welcome everyone to today's session of Seminario Flotante. Our invited speaker today is Laura Gamboa from Universidad de los Andes, and she will be talking about dynamical operators and topological partition models with evidence. So thank you, Laura, for accepting our invitation, and the screen is all yours.
Thank you, Dario, for the invitation. Okay, so my plan for this talk is the beginning, give you like a very brief overview on the basics about the logics for knowledge and belief. Well, epistemic logics is the logic for knowledge and belief. It traces back to Aristotle, but okay, but this is not a working philosophy, so it only goes back to the late 50s or so, right, where the first work on formal epistemology were made. And then, yes, and I will talk, the word dynamics means that the knowledge is changing. So it's about like the change of the knowledge. So I will tell you a little bit about the basic of the most basic dynamics that we care about, that is the public announcements, and a little bit on logics for knowledge and belief, right? So I'm gonna start only with knowledge, logics of knowledge, and then introduce the notion of belief together with the knowledge, notion of knowledge. And then I will talk about the models for and the logics for evidence-based belief. So which is a different approach to think about the logics of belief, right? And yes, and I'm trying to answer like the very natural questions when we try to do dynamic operators on multi-agent models for topologically based evidence-based belief. So right, let's move on with this, shall we? So the basic epistemic language, the first one that was introduced in this topic by Jaakko Hintikka back in 1962, if I'm not wrong, is this multimodal language given by, we always start with a countable set of atomic propositions. So everywhere when you see a P, Q, letters P, Q, R, denote those propositions, and a fixed finite set of agents, AG, of nameless agents. So everywhere where you see letters A, B, C, those are agents. Then we have this language that is like an extension of the propositional language, where you add a modality, K sub A, for each individual agent, right? So the formulas of this form, K sub A phi, are read as agent A knows phi, right? And these modalities, you should think, maybe to give you an idea, like a for all, like a universal quantifier. So we do almost always care about their duals, right? And this is the abbreviation that we take for the dual, just as in the case of the first order logic. So this is like an existence quantifier. Yes, and we use abbreviations for the our basic set of connectives are the negations and the conjunction, and so we use abbreviations for the disjunction, the implication. Here I forgot the double implication, the true and the false. Like we can think this as zero arity connectors. So, but you can think this as take any propositional tautology, zeta for true and the negation of this one for the false. So yes, this is the basic epistemic language. Epistemic formulas and the relational semantics for them are interpreted on pairs MS that are called epistemic states. So this is a pair consisting of a Kripke model. This is simply a non-empty set W, a binary relation for each one of the agent over W, and evaluation. Evaluation here is just a function assigning to each proposition, each atomic proposition, its true set. Those so the set W is known as the set of all possible words or as our universe. I will sometimes refer to it as the universe. And here you're just saying to each letter, you're just assigning a subset VP of W. So you're saying those words where P must be taken true, and when the words that are not in here, there the value is false, right? So we will say exactly that. So the first clause for the validity of a formula in an epistemic state is just that. Then the negation is true if and only if the formula itself is false in an epistemic state. The conjunction the same. So the conjunction of two formulas holds in an epistemic state if and only if each one holds. And then we will say that at an epistemic state S, the agent A knows phi if and only if. So these binary relations are also known as accessibility relations. So to each word that the agent can access from S, in each one of them, the formula phi also holds, right? And we sometimes say we do actually care about the validity of a formula in the whole model M. So we will say that phi is globally true in a model if it is true at every point, at every epistemic state in this model. So, and this is denoted just like this. So it's more like the notation that you already know for the first order logic.
So how do you read the fourth one? MS is KA if and only for every world.
Yeah, for every accessible world to the agent. For the agent, yeah,
is this read like a modality or like a?
It's a modality. Yes, exactly. Okay. Just like the necessity.
Okay.
Yeah, and it's a necessity modality. Yeah. So a first example for this will be the 3-player card game. So there are 3 players, Aim, Bill, and Katie, and each one has drawn a card from a stack of 3 cards, 0, 1, and 2. This is all commonly known to all 3 of them. However, only each agent only knows which card they have drawn. Yeah, I think I did something wrong while typing this. And so suppose that in reality, Aim has card 0, Bill card 1, and Katie has card 2. So if we write in just like a string, 0, 1, 2, for the DL of cards where Aim holds card 0, Bill has card 1, and Katie holds card 2. Then notice that Aim, she only knows that her card is card 0, so she cannot distinguish between these 2 deals, right? And whereas deals 0, 1, 2 and 2, 1, 0 are the same for Bill, because Bill has card 1. So this example can be represented in by this following epistemic model, right? So there are the 6 possibilities that there are in the game. I have just underlined the current state, like the one that is representing the reality. And there is a binary relation. Those are for each one of the agents. So A is for Aim, B for Bill, C for Katie, and exactly like, and they are actually an equivalence relation. They cannot distinguish between some pairs of possible words, right? So I just omitted here the self loop for each one of these states. And facts here, so our language, and like a nice language for this one, is based on atomic proposition of this form, like a number and an agent. Meaning that this agent holds the card with this number. So with that in mind, in this epistemic state, right, this one, it holds that Aim knows that Bill doesn't know her card. Yes, as this is, which is expressed formally, but exactly this formula. She also, in this case, Aim also doesn't know which card has Bill or which card has Katie. So these are like the kind of models that we are thinking here. They are a little bit hard to just get used to them at the beginning, but like as the ways I think it is just try to look at the situation as an outsider instead of as a player, each one of the players. And then think of like try to get in the place of each one of the players. And that's what gives you the relation here, right? So one may wonder, what are the axioms, like those rules that must always hold for knowledge, right? So here I have 4 of the most commonly known axioms in modal logic, which are axioms K, T, 4, and 5. So if we look at the first one, for instance, this is saying that if agent A knows that P implies Q, then if agent A knows P, then naturally agent A must now know that Q. So this is meaning that the agent knows all the logical consequences of its knowledge, right? The second one, axiom T, that is this one here, is just meaning that if agent A knows P, then P must be true. So everything that A knows is true. This principle is also known as truth principle. The axiom 4 is very interesting because it is saying that whenever an agent knows something, then the agent itself knows that he knows that about that thing. Yes, so it means that agent A knows what it knows, and this principle is also known as positive introspection. Like the agent has some introspection about what they know. And axiom 5 is very similar to axiom 4, but changing, like if an agent doesn't know something, then they know that they don't know something. So agent A knows, it does not know. This principle is also known as negative introspection principle.
So
yes,
most
Andres?
people do not satisfy that axiom.
Exactly,
5.
exactly. So the work, that was done by most of the philosophers in this area, but Hintika, Stolaker, and so on, back in the 50s and 60s mostly. So for most of them, when you try to represent how like normal people think, they only take the first 3 of them. However, for some applications, we can consider also adding the axiom 5. Yeah. Sometimes those agents, when I talk about agents, I'm not talking always about people. Sometimes they are machines. And when they represent machines, like, I don't know exactly why, but they like to use also axiom 5. Yeah, that's how there are theses like defending axiom 5. And actually Hintika himself did a nice job trying to defend this axiom 5. Yes.
Laura, and the numbers, what do the numbers correspond to?
So I don't know exactly, but okay, like that's more of like in the history of modal logic, they were trying to, like, just as in topology, you have axioms T1, T4, T3, T2, and so on, trying to getting closer to metrizable space. They were doing something very similar to that, but I don't know the full details.
Okay.
Yes. And then to get a deductive system, you need also inference rules. So the 2 rules that are like commonly used are modus ponens. I think we all know about this one, and the necessity. So this is like the generalization rule for first order logics. So from phi, infer KA phi. So infer that the agent knows phi, right? So somehow, if phi is and yeah, if phi is a theorem, then agent A knows phi is also a theorem. So the basic logic of all frames, of all these frames, of all Kripke models, I should say, because I didn't introduce frames, sorry, is axiomatized by all substitutional instances of propositional tautologies. So as we can use propositional tautologies such as P implies that Q implies P, then we can replace propositional error for any formulas in the language, and this will also hold, right? So that's what it means. And this is the basic logic K, and yeah, and that's the axiomatization for the logic of all Kripke models. Then, if we want to hold also axioms T and 4, that are like the most natural ones for how the human mind works, you must take models where the accessibility relations are transitive and reflexive. So actually, axiom T is capturing reflexivity and not transitivity, and axiom 4 is capturing the transitive property. And when one can want to consider also the negative introspection principle with the other two axioms, T and 4, you get the logic S5, which is the one corresponding to models with equivalence relations for each one of the agents, right? So this is like the very most basic modal systems that we should always know about. So this is the basic. So sometimes for some authors, they consider epistemic models to be models of S4, and sometimes they consider epistemic models to be models of S5. And what should we think always about this is that in S4, you're taking transitive and reflexive relations, and in S5, you get partitions, right? So this is like the idea. Okay, and now let's move to the dynamics on epistemic logic. So dynamic epistemic logic is the logic of knowledge and how the knowledge change. So this can be described as the study of how agents update their knowledge and even change their belief on the basis of pieces of information they exchange in various ways. Like the most simple way to achieve this is by announcing to all agents simultaneously about a fact that must be treated as truthful, right? So this is the most simple action you can think, and this is called a public announcement. So if going back to the 3-player card game, it may happen then after each one of the players have taken their respective cards that we already know that A now says, I do not have card 1. And yes, this is true because Bill has card 1, so it is not possible for A to also have the very same card. Those cards are not repeating. So let's explore how this announcement changed the epistemic state from the original one. So we were in this epistemic state, it was the original setting. So A's announcement corresponds to this formula here, the negation of 1A, right? So 1 is not the card that N has. This announcement, what we'll do now is it will restrict the model to those states in which the formula is true. So after you have been, if you are any of these players, and after you have been told that N doesn't have card 1, then you are simply going to discard this state and this other state, right? So we will end up simply with the following epistemic state. So now the new model has only those worlds where the formula that N announced is true. So in this new epistemic state, as we might expect, now Katie knows that N holds card 0. Yes, because Katie has card 2. So she knows that N must have either card 1 or card 0. So, and if it is true that N doesn't have card 1, then she must have card 0. Even though N doesn't know that about Katie knowledge, because she also considers possible this word that is down here, where no, this is not the word, it's this one, sorry, where Katie holds card 1. So if these were the actual word, then the announcement wouldn't have any new information for Katie. And this is exactly what happens for Bill in this state, because after N announces she doesn't have card 1, Bill may be thinking like, yes, I didn't already knew this because I have card 1. So it is not possible for N to have the same card as I have. But yeah, so this is the idea. So what we're gonna do now is that we're gonna enhance our language with modalities, and this can be think as modal operators for every formula. So in any case that we have two formulas, phi and psi, we can announce phi and then see if psi holds after the announcement of phi. So we're gonna add formulas of this form now. And those are read as after public announcement of phi, it holds that psi. So the effect of the public announcement of a formula phi on an epistemic model will be the restriction to those states where the formula holds. And this also applies to the accessibility relations between the states. So in this sense, announcing phi can be seen as an epistemic state transformer. It transforms the current epistemic state to a new one, corresponding to what is called a dynamic modal operator. This modal operator here. So you just put the formula inside some nice square parentheses and inside some brackets with this exclamation formula, right? So if we have a model, M, once again, an epistemic model, this can also be taken as an S4 epistemic model. It will not change. We want to obtain a new epistemic model that reflects this change of announcing phi, right? So we must now first define the truth of a formula in the enhanced language, being true as an epistemic state given by our word S, by extending the truth definitions for formulas in, well, the smaller language with only the modalities for knowledge with the following rule. So in the state S, after the public announcement of phi, it will hold that psi. If and only if phi being true in this state implies that in the new state, in the new model, and the state that is obtained after this dynamic, it holds the formula psi. And this new one is simply the restriction, this new model that you obtain after the announcement of phi is simply the restriction of the original model M to the truth set of phi. So yes, this is like we can think as the set that is defined by the formula phi here. And yes, and the set of all valid public announcement formulas in the language, I will call this just the PA, which is the public announcement logic. And so, and the logic for this logic is very well known, right? We do know a proof system for the public announcement logic.
A question, Paola. Laura,
yes,
what
Javier.
happens? ¿Qué sucede si? What happens if the restriction is empty.
Yes. Well, this will always be true because of this part will always be false. But we try always to consider formulas that are satisfiable in the model. Yes.
Okay.
Yes, we don't want to end up with empty models, but it doesn't matter because those formulas will always be true. Yes. So the proof system is very well known. So you just start with the axiomatization for the epistemic logic you're considering. It can be the S5 or the S4B epistemic logic. And then you have to add this set of 5 axioms and the necessity rule for each modality of announcement, of public announcement. So there are, now we have like infinitely many rules here. And what is very interesting about these axioms and is that I'm calling them the reduction axioms, is because they allow you to translate every formula in the enhanced language to a formula in the smaller language, only with the knowledge modalities. And this is actually used in the proof for this system. And most systems in dynamic epistemic logics use this very same principle. So yeah, some of them, we can maybe explore some of them. For instance, the atoms axioms is telling you that after the public announcement of a formula phi, P is true if and only if phi implies P, right? Because the evaluation was the same valuation, but in the restricted model. And so far and so on. Like those are very, the next ones are very similar to that one, except for the one for the conjunction. This is just a distribution over the conjunction of 2 formulas. And the last one is the one that actually allows you to find, to use inside here formulas of the whole language. So this phi can be also be a formula with these announcement modalities, right? So this is the one that actually makes this translation to make sense and to be very well defined. But yeah, so I'm not gonna enter into the details, otherwise I will not get to the point that I wanna get with this talk, right? So yes, and theorem, this is known that to be a complete axiomatization for those models. So now let's move to the logics for beliefs. So I want to start just with a simple like daily life example, which is the following statement. We says, John believes today is Tuesday, although it is Wednesday. So this seems to be completely reasonable. However, if we replace the word believes with the word knows, then we end up with a phrase that does not make sense for us, because it is not possible for a person like, you know, in this world, a person that, I'm assuming that John is not living out of the city or somewhere that he can get lost, you know, in the time. But like, we know for a person, let's think that John lives in a city, that it is not possible for him to be sure on his knowledge that today is Tuesday, although it is Wednesday, right? So what is the difference here? So we're now again asking for a larger language that where we also add modalities for belief, right? And exactly the formula BA phi is whereas agent I believes phi. And once again, we might consider the dual official modality as an abbreviation, which means something like it is consistent with A's belief that phi can be true. So the previous example is exactly showing that property T. So this property BA phi implies phi does not hold for beliefs. Everything that you believe is not necessarily true, completely true. However, if it is often assumed that belief sentences should be at least consistent, which is captured by the following axiom, axiom D. This is not the only way we can consider this, but it's saying that like you cannot believe in something that is true, is false, completely false. This axiom is weaker. So axiom T implies axiom D. But axiom D does not, you cannot gain axiom T from axiom D. So yeah, it is a weaker axiom. And so the proof system for the logic of knowledge and belief, where you try to capture like the idea of having very like non-stupid beliefs, are that the beliefs must be somehow consistent with your knowledge, right? So this proof system was given by Robert Stolnaker, where he considers that one may not accept axiom 5 for knowledge, actually. So he starts with only the axioms K, T, and 4 for knowledge. And they add the following axioms that most of them combine the two modalities, right? So the first one is the positive introspection for belief. So if you believe in something, then you know, you are aware of your beliefs. And if you don't believe in something, then you are aware that, like, you know for sure that you don't believe in that, right? Also, knowledge must imply belief. Otherwise, you will believe in something. Otherwise you will know, no, you will believe in something you don't know, I think. The fourth axiom here is called consistency of belief. This axiom is well, actually, yes, this third axiom allows us to have the derived rule of necessity. So from phi, you derive this, but then consistency of belief axiom will be equivalent using this rule and modus ponens to, and actually, yes, this also implies that you will have the K axiom for belief, that to axiom D. So this is, you can deduce from this one and from D, the axiom D I presented you before, this fourth axiom. And then we add the fifth axiom, that is the axiom for strong, that is called a strong belief. So if you believe in something, then you believe you know about that, right? I don't know, I have my thoughts about that. Like, I still don't get how the philosophers came by with this strong belief axiom, but we're gonna accept that here. I'm gonna believe on them, on their knowledge, and that's it. So this system is I will denote this by Stoll in honor to the philosopher Dr. Stolnaker. So what is known about this system is that the formulas with only the belief modalities that are derivable here are exactly the ones that are derivable in this system, KD45. So this is the system where you consider the modus ponens rules, the necessitation rule for belief modalities, and axioms K, D, 4, and 5. So those four axioms that those four letters represent over that language. More interestingly, it holds the following, that you can deduce that believing in phi is the same as not knowing you don't know phi. So belief is actually definable in the smaller language with only the knowledge modalities. And also, we have this axiom here. So this theorem here. So not knowing you don't know phi implies you don't know the negation of phi. This last one, if we consider it as a sentence, it's known as the point to axiom. And what will happen is that in the system, if we replace BA with not knowing you don't know, we will have an S4 point to logic, which is the one obtained by adding the point to axiom to the logic S4. So yeah, this is what is happening here. Right. This will be important later. So this is why I'm telling you about this. Right, so next I'm gonna move to the logics for evidence-based belief. So now we're gonna base our beliefs not on what we already know, but on evidence that is available for the agent. So this is more of how, I don't know, when you're doing science, you have some information, then you become to a hypothesis, or you believe this is true, and then you add new information, and then you will try to see if that is true later or not. So this is kind of the idea. So there are the first kind of models that we have here is what are called the evidence model. So it is a tuple with, again, a non-empty set of words W, evaluation B, but instead of having a binary relation, we will have an evidence function. So at each word W, you will have a family of subsets of W, right? Which we are going to call pieces of evidence. So these are the pieces, EW are the pieces of evidence that are available for an agent. Here I'm talking that I'm thinking that there is only one agent involved. And these are the pieces of evidence that are available for this agent. And the pieces of evidence must follow these two conditions. The first one is that we cannot have pieces of evidence that are empty. And the second one is saying that like the agent knows its world, its universe. So the whole universe is a piece of evidence, always. And here, instead of epistemic state, I'm gonna talk about pointed models, which is just the same, a pair of a model and an actual word W. And when E is a constant function, because it may happen, we will get what we call an uniform evidence model, and I will write as E0 instead of E. So yeah, although this may seem like we are losing a lot of generality, these uniform evidence models are more interesting than one may think. Right. So in this case, we will have a language that will let you think about beliefs and evidence. So we have three modal operators here. The B1 is the belief one. So B phi is read as the agent believes in phi. Then we will have the evidence of modal operator, which is the square. So square phi is read as the agent has evidence that implies phi, right? And we will add now, and this is called a universal modality. So for all phi means that phi is true at all states, right? I'm not sure what has motivated, the authors to add this universal modality, but it is found everywhere. So I'm not sure why they have added this. I'm trying to learn about that more, but yes. And the duals for three modalities, for the belief modality is the same as before. We just added like a hat above the modality. But for the box modality is the diamond, and for the universal modality is the existence modality. So yeah, just as we might expect about this. Otherwise, this will confuse everyone. Right. So in an evidence model, the truth of a formula is defined by the following clauses. So for atomic propositions, we already know how the formulas, if an atomic proposition is whether it is true or not. For the negation of a formula, we use the same as before. For the conjunction of two formulas, we use the same as before. Now, we will say that in an epistemic state, we can think this, or in a world W, the agent has evidence supporting phi. If there is a piece of evidence available to the agent, such that in all points of X here, in X, it holds that phi, right? So this can also be written in the following way, and this is that X is contained in, and I will now introduce this notation, in the truth set of phi in this model, right? So these double brackets will denote the truth set of phi. So this is exactly the points where this is true, phi is true. Yeah, so this is like, if you read this one, then this is the reason why you don't want empty sets to be pieces of evidence available for an agent. Then you will believe in phi if and only if for each. So you can take families of pieces of evidence that has the finite intersection property. So you will look at pieces of evidence that you can put together safely, so they are consistent. And then you take the maximal one, take the whole intersection, and see if whether or not the whole intersection is once again contained in the truth set of phi, right? But this intersection, so can be, and of course, as we know, if W is not finite, this intersection can be empty, right? However, these models were like motivated in the finitary case. So in the finite models, every finite model will validate this formula. So that if the agent has some piece of evidence for anything, then they cannot believe in something that is false, because families with the finite intersection property of subsets from a finite model cannot have empty intersection, right?
Laura.
And yes, Javier?
Laura, question.
Yes.
But even in the infinite case.
In the infinite case, we will have problems. I will show an example.
No problem, because if the intersection is empty, anyway, phi is valid because it's an empty condition.
No, but what will happen is that
if because the implication is true.
If this is false, this will be contained in the truth set of the falsum. That is the empty set. So you can have inconsistent beliefs.
Okay.
Yes, this is a problem, and I'm gonna show you like the very canonical example for this. And of course, the for all formula is true at any point, if and only if it is true everywhere. So this is just like the intended semantics for these formulas. And yes, of course, when we have an uniform evidence model where all maximal FIP families have empty intersection. So consider this one, the universe is the set of natural numbers, then your evidence sets are the unbounded intervals. And we don't care about the valuation here, so you may think as the valuation as a constant function with the empty set. So no atomic proposition is true anywhere. So the only maximal FIP family here is all is zero. However, this intersection is false And then this will be contained again in the truth set of the falsum. So here the agent will have an inconsistent belief. In other words, this means that axiom D fails in this model. And the above observation is telling us that this logic does not have the finite model property, since in this model, like all pieces of evidence, actually this is not very important, that are not empty, but any piece of evidence is a subset of the whole universe. So this implication is false. And why we care about the finite model property is because if a logic has a finite model property, then it will be decidable, which is, well, very interesting, because it will be interesting for several applications. So then we will move to topological evidence models. So this is another view to uniform evidence models. So fixed and uniform evidence model, here M, a body of evidence will be a family of pieces in which every non-empty finite subfamily is consistent. That is the same as having a set with a family of subsets with the finite intersection property. A combined evidence is a non-empty intersection of finitely many pieces of evidence. So what you are doing is you're closing this E0 under finite intersections, like non-empty finite intersections. And these are now this set E, you define this E as your set of pieces of evidence now. So maybe you can see here the idea that we are getting around. What happens is that if you take the union of all E0, this will be W, the whole universe, because W is here. And then this E will be a basis for a topology over W. This is a way to construct topologies. So what we are going to do here is that we will introduce topological evidence model or topo-E models. So this is just a structure. And there are two ways to see this. The first one is that, okay, you start with a uniform evidence model, W is 0B, and then take the topology generated by E0 or by E. That's the same topology. So this is the smallest topology, making the pieces of evidence open sets. Another way to see this is that you start with an topological space W tau V plus a subbasis for the topology E0, right? So we will say now that a combined evidence, or simply an evidence, which is this is a basic set E, supports a proposition. So you can think of a proposition like the truth set of any formula if it is contained in P. And the intuition now is that these evidence that are contained in the subbasis represent the most basic pieces of direct evidence. So you have your pieces of evidence, then you close under finite intersections, you have a basis, and then you get the topology. This is nice because in these uniform evidence models, you cannot believe in something that is false, as we may see now, yes? So the topological language will be one that is very similar to the one I already showed you. So this is the belief. We already saw this universal modality and this evidence modality. Now we're gonna add up a knowledge modality and what we is called like basic evidence modality. So for the formulas here, we will define the truth, the word X, And here I'm using X instead of W because for me, points from a topological space are always called X, cannot be called P because P are propositions. So here, what we're gonna start, I actually put this in no important order, so, and that was a mistake, but yes, so the truth of for all phi is the same as before. So this is true if and only if the truth set of phi is the whole universe. You will believe in phi at our X if there is no pieces of evidence that are inconsistent with phi. So this means that the interior of phi is dense, right? So you don't have open sets that are disjoint to the interior of phi. So this is why this makes sense. So this is called the dense interior semantics. And at our X, you know phi, if not only the interior of the truth set of phi is dense, but also it also must be true that X is an interior point of the truth set of phi with respect to this topology tau, of course. And also, you have evidence, you have basic evidence supporting phi at X if there is an open set from the sub-basis containing X and that is containing the truth set of phi. And you have evidence supporting phi if simply you just take this same definition, change E0 with E. That means there is a basic open set containing X that is containing the truth set of phi. So then this is, but we all know that this is the same as being an interior point of the truth set of phi. So this is actually called the interior semantics. And actually, if we go back in the history of modal logics, this kind of semantics is older than the relational semantics that Kripke introduced. And they were studied even by Tarski back in the 1940s, something like that. But yeah, this is it. So now, yes, let's take a look to the following proposition. This is saying that the following equivalences are valid in all topo models, topological evidence models. So this is that we are once again, if you look at this, we are once again in Stolnaker's logic. Basically, this is what it's telling you. But not only that, but look here, it is also telling you that belief is definable on these two modalities, the universal modality and the evidence modality. And the same will happen for knowledge. Knowledge is also definable with these two modalities, right? This diamond is the dual of the square modality. So you can give a complete axiomatization only by giving a complete axiomatization for the fragment with only those two modalities. So it is known, this is due to Tarski actually, and another logician, I don't remember his name now, that for the interior semantics, you have the S4 system, like the S4 axioms and rules for the interior modality. And then because we have also the universal modality, you must add the S5 axioms and rules, and this axiom connecting the two modalities. And also, what the second theorem is telling us is that, yes, if we look only for the fragment with knowledge, for knowledge and belief, this can be axiomatized with the same system from Stolnaker that we saw before. So yes, belief is also very strong here. And I think that's the reason why that last axiom was called a strong belief, because it makes it completely definable in terms of the knowledge of the agents. Right. So now we are going to do dynamics on these evidential models. So the first dynamics are public announcements. This has been very well studied. I'm not going to show you the axiomatization at this point because I don't have enough time for this. I knew that beforehand. And yes, here the semantics is the same as before. So at X, it is true phi will hold after a public announcement of psi will be true after a public announcement of I, if and only if is true, then this implies that in the updated model, psi is true. And the updated model is exactly defined the same way as before, just the restriction. We only have to be careful when intersecting basic evidence sets that they are not empty. So we're removing all those that are not compatible with a proposition P, right? So yes, here P will mean P is the truth set of phi in M. But we can also think of dynamics that change the evidence that is available for the agent. So there is this dynamic where I don't know, maybe you can think that the agent is a person that is trying to investigate something, and then its boss tells him like, hey, take this new piece of evidence and add it to your basic evidence. So we are changing the sub-basis just by adding P to the sub-basis. And the semantics is as follows. So after accepting P as a new piece of evidence, psi will be true if and only if the truth set of phi being non-empty implies that psi is true in the updated model. And here, the only changes we have to make are in the topology and the subbasis of the topology. There is another you can consider that this is the action of incorporating P. This is the evidence upgrade. So you add P to all of your basic set of evidences, and the semantics is just as the one before. And you must now take the topology generated by this set, that if I'm not wrong, is just adding P to any open set. And these all have been well studied. Now, one may wonder, how can we do this with several agents? So it is not as simply as having a bitopological space. That will not work, that has some problems, but the solution that Baltak and his colleagues came by a couple of years ago were that you need not only two topologies, one for each agent, but two partitions. And those partitions, only to make everything easier to prove, are consisting all of open sets in its corresponding topology. So those are partitions of open sets. And this definition is a very technical one, but we will write PIX for the unique cell in pi A, pi I, where X is in pi. And a set will be said to be locally dense in an equivalence class if the equivalence class is containing the closure of U, and of course with respect to the respective topology. So here, the knowledge operator will be defined the following. So once again, X is an interior point, but now we will ask to the interior of the truth set to be locally dense in this equivalence class. And here, this is nice because the proof system is just take the proof system for each one of the modality and add two of them, like take all the axioms and all the rules, put them all together, and that's it. Sorry. And you can also add modalities just as before, like universal modalities, but these are going to be a little bit different. So we need one for each agent. Evidence modalities and belief modalities with very similar semantics here, just adding the locally dense condition here. So in the universal modality, you will not ask the whole universe to be contained, but only the partition set containing X to be contained there. And the axiomatization is just by taking all these different fragments once again and taking the axioms and mix them all together. So the natural and open question now is, what about evidential dynamics on these topological partition models? And what I think works fine, so the axiomatization is obtained by adding the correct axioms together and nothing else, will be with the following dynamics. So for updates, it's the same as before, just taking the restriction. For evidence addition, we must addition evidence to a single agent at a time. See, this is very important. So if you are adding addition to a fixed agent, then you let the other topology just as before, and here just add P as a piece of evidence, and the partition will be the same in both cases. And what I think will work for the evidence upgrade, sorry, I made here a mistake. This is upgrade. And this is just the last slide, no worries. Is that you must not only add P to each open set, but you will also have to change the partition. So here, you will take the original partition and take those sets that are not containing P, this is what it's saying, and remove P, and then add P as part of the partition. However, this partition will not consist of clopen sets. So, but this is not a restriction, like a real restriction for this kind of models. You can also work with, it is possible to work also with regular partitions. And yes, that was all. I know I was very short of time.
Okay, Laura, thank you very much.
I don't know if there are any other questions.
Yeah, are there any questions for Laura?
Do we have time for questions?
I have time. I have plenty of time.
Okay.
So.
No, I just, there's something that may be related, remotely. So Hodges is going to give a lecture. I sent it to the logic group here in Bogota, but I think it is because it is about the early birth of modalities 1,000 years ago. So Avicenna kind of discovered when he was a teenager.
Yes, I remember that.
It's kind of very unique. And Hodges once told me that Avicenna was not really translated into Latin, so it was only in Arabic, because he got a bad review from Averroes in Spain. So somehow, of course, everybody read Arabic. Everybody who knew logic read Arabic at the time, but at some point, that's kind of shifted to Latin in Europe, and Averroes was kind of part of the transition. And essentially, he gave, apparently he didn't understand the novelty of the modalities in Avicenna. So he said, well, he kind of contradicts Aristotle or whatever, and he doesn't say. So the result was that it was not it is not translated into Latin, nor in English, nor anything. And Hodges has been working on that. So he is learning Arabic still, to do this translation. So I think it'll be interesting for historical reasons. Of course, I mean, it is very different from what you are working, of course.
Yes.
But Hodges kind of combines the modern perspective, especially model theory, with his analysis of Avicenna. So on Monday, he's going to speak in the Nordic seminar. That may be, just...
Yeah, I'm looking forward to that talk, actually, so yes.
I'm very intrigued. At some point when you started looking at your FIP, and yes. This, before you got to topology, so the Borovic and Katz have circulated I think it's a preprint, very recent, which is kind of basic but very nice. It's on belief systems, on voting systems, for electoral processes and ultrafilters. So he says, I think it's called something like are infinitesimals necessary, or infinitesimals, and it's something about infinitesimals that he's interested in. But he does Arrow's impossibility theorem, in voting systems. And what struck my attention when I was listening to your lecture is that somehow he starts by doing this kind of a double power set that you have at some point, but he goes to ultrafilters, and then he says the possibility of going to an ultrafilter is kind of the possibility of making coherent a lot of beliefs when you have like millions of people who are going to vote, like for a president or for some election. So each one has their own beliefs or knowledge or whatever. They can be manipulated, that's another story, but there are sets that somehow have effect on elections, and there are sets of people. I mean, I myself have zero effect in the election in my country.
No, but there are models for, like, I know that there are people that are working for models of social interactions.
Okay.
Knowledge and belief. I know.
Creo que podemos pasar español.
They try to use the idea of a
está
social
Sergio Lara
network.
y nosotros,
Yeah.
Darío. Es interesante porque prueba el teorema de imposibilidad de Arrow, da una prueba muy, muy elegante, muy bonita con su sistema como de conjuntos relevantes de votantes. Y prueba además que la única manera, ese es un teorema terrible, el de Arrow, que lo único que realmente termina decantándose son los dictadores. Entonces es una cosa muy, muy brutal, pero hay una demostración ahí usando, es básicamente el teorema de Walsh, no es más que el teorema de Walsh. Pero vale la pena, es muy reciente, Laura. Ese salió ahorita, es Borovic y Katz, son los autores. No es lo mismo, pero de pronto tiene que ver. Entonces, chévere como comparar un poco ahí.
Yo la verdad es que yo a todo le siento un sabor parecido.
Sí, pero ahí los detalles son los que pueden.
Sí, los detalles juegan
diferencias.
un papel muy importante. O sea, nomás como las pruebas para cada uno de esos sistemas.
Sí.
Siguen esquemas no muy diferentes a los que uno usa para trabajar lógica en primer orden y esto.
Sí.
Pero los detalles son muy interesantes. Y siempre hay un punto donde hay que hacer algo diferente, o si no, uno se queda atascado. Es increíble.
Ahora, hay una especie de discusión, y seguramente Darío tiene algo que decir ahí también, que es la discusión que hay actualmente en computación entre si una máquina aprende porque uno le enseña, que es más o menos como estos axiomas, el cada 5, no sé qué, o sea, uno le da como uno, o si la máquina aprende porque ve millones y millones de casos tan rápido que puede como sacar ahí una especie de conocimiento y puede además iterar y comparar y hacer tests con respecto a lo que le dicen que está bien, que es básicamente lo que sucede en Machine Learning, dicho de una manera supremamente elemental. Pero de alguna manera la discusión, y esa discusión la da muy bien al que le dieron el premio Turing el año pasado, Jan LeCun. Él dice, en realidad parece que los procesos de aprendizaje más efectivos, de pronto también en el ser humano, no son con axiomas, sino son casi como con ensayo y error. Es una cosa muy brutal decir eso, pero muy loca.
Con ejemplos.
Con
sí. Ejemplos.
Exacto. Y es muy duro eso, porque entonces uno se preguntaría, bueno, está todo este sistema de knowledge, belief, de conocimiento, creencia, que lleva siglos siendo axiomatizado, y en los últimos, no sé, 50 años, pues con los que mencionabas ahí y todo eso, se ha vuelto mucho más sofisticado y topologizado y todo eso. Y está toda la teoría del learning, que ni siquiera ya es machine learning, sino puro learning como lo que hace Mariante Maliaris y gente así con pura teoría de modelos, pero estabilidad, pero poniendo la estabilidad a jugar un poco más como haciéndole preguntas a una máquina. O sea, la máquina hace preguntas. ¿Es cierto que estos son letras A o son letras R, digamos? Que parece como una pregunta muy boba, pero que se puede formalizar en alguna lógica como primer orden o algo así de pronto. Y lo que hacen es mirar las clases de preguntas que uno puede hacer cuando tiene una teoría de primer orden, por ejemplo, y mirar si la teoría es NIP, o si la teoría es estable, o si la teoría es superestable, o algo así, y ver como que, y empiezan a mirar, pero eso está en un dominio totalmente distinto de este. Y la pregunta que yo me hago es, ¿será que de alguna manera hay algo de pronto ya hay alguien mirando eso, como la conexión entre aprendizaje, creencia, en toda esta línea eh, muy, pues, muy ilustre, muy pesada de los trabajos que mencionaste. Y por otro lado, esta otra cosa que parece venir de otro lado, de los ejemplos y de correr máquinas muy rápido y poder hacer preguntas. Y hay quienes dicen que solo lo segundo funciona. Yo no creo que uno pueda, o digamos que sea tan fácil decir que es una cosa o la otra, pero sería interesante poder comparar, por lo menos. No sé si Darío quiere, porque Darío conoce muy bien
Yo
esos
creo que
temas
sí hay
también.
trabajo por ese lado. Yo creo que sí. Me suena que sí. Algo he leído. Pero
Y
es
yo
muy
no tengo nada que
reciente.
aportar.
Sí, no. Es súper reciente. Pero
Ujú.
así, no sé, más reciente que el tinto que me acabo de tomar. O sea, una vaina absurda. Sí. Yo sé que sí hay. Pero no, pues tampoco he leído mucho por ese lado. Sí.
Interesante, súper interesante.
Yo tengo una pregunta, Laura. O sea, al
Dime.
final cuando tú decías como, o sea, que esas ideas que estabas tratando funcionaban, tenías esas definiciones, ¿cierto?
Sí.
Lo que tú
O sea,
quieres es
lo que
lograr
quiero
probar
hacer es que,
soundness y completeness, ¿o
exacto,
qué es eso?
soundness y
¿Cuál es?
completeness de pegue los axiomas de aquí y de allá.
Ujú,
Eso es
ok,
lo que uno quiere hacer. Que eso es justamente lo que falla cuando uno pone simplemente dos topologías. Va a haber una fórmula que es válida siempre, pero que no se puede deducir.
ok,
Porque, claro, cuando yo agrego los axiomas y las reglas para cada modalidad
por
independientemente,
separado. Ujú,
por separado, yo no puedo deducir, no voy a poder deducir ciertas, o sea, bueno, sí, uno puede hacer sustitución de fórmulas, sustitución uniforme de fórmulas equivalentes, eso sí lo puedes usar, pero nada más. Sí,
ujú.
entonces se vuelve como las únicas fórmulas con dos modalidades que puedes probar ahí son las que son, hágale la sustitución a algo que ya probó, que
Sí,
solo
exacto.
tiene una modalidad. Entonces, así es como uno juega, realmente.
Ok.
Sí, entonces ese es como el juego, a ver en dónde no falla. Y pues hay como un par de ejemplos como las fórmulas que fallan en los modelos solo con dos topologías, entonces uno trata como de coger ejemplos parecidos y ver si siempre son verdad o no.
Ujú.
Sí. Y
Pero
pues
tú, pero o
es
sea, a
mucho
final
más
de
difícil de lo
cuentas
que uno
esperas hacer
cree.
una demostración, ¿cierto? Una
Eh,
prueba formal de que el nuevo sistema es...
o al menos conjeturar un buen modelo de que...
Ok.
Yo creo que más que todo para el de Evidence Upgrade está súper complicado. Ese Evidence Upgrade me ha dado como vueltas tranquilamente 3 semanas así, dele vueltas al problema y nada.
Ok.
Ese es el más complicado. Sí. Los otros dos son mucho más fáciles de trabajar, pero mucho, como brutalmente más fácil. Sí.
Oye, tenía otra pregunta, pero eso sí es por ignorancia mía. O sea, ¿qué significa que una
Sí.
lógica tenga o no tenga la propiedad del el finite model property?
Ahí,
O sea, porque yo sé que significa en teoría
básicamente es,
modelos, pero es que que
pero es
una
igual, como
teoría
que
tenga.
exacto, cualquier teorema que no se puede deducir encuentras un modelo finito donde su negación es válida, sin estimar.
Ah, uy,
Wow.
ok.
O sea, es un poco más
Es,
fuerte, esa es un poco
Sí,
más
sí, sí,
fuerte.
ya
Y
entiendo, ya
por eso
entiendo.
justamente es interesante porque te
sí,
permite dar decibilidad y te da un orden en la decibilidad porque tú dices, claro, el modelo se construye de esta manera y entonces como tiene tantos,
Ujú,
está así de grande, no sé qué, entonces la complejidad está acotada por tal función.
ya.
Entonces es un poco más fuerte ahí. No es muy diferente
O sea,
a
cualquier cosa
tener
que no sea, digamos, una válida, digámoslo así, es porque hay un modelo finito que la
que
niega.
satisface la negación. Sí,
Está chévere.
sí, entonces uno construye el modelo. Ese es justamente lo que uno quiere hacer ahí. Entonces, por
Ujú,
eso le da decibilidad y pues uno quiere decibilidad para aplicarlo en distintos contextos. Eso es muy utilizado en computación. Entonces, uno quiere
ok,
decibilidad allá, justamente.
listo.
Sí, Pi.
Hola,
Sí, ahí es, no es muy
Hola,
diferente.
Sergio.
Sergio.
hola Darío, hola Andrés, hola
hola.
Laura. Mira, yo quería hacerte una pregunta, sobre
Ajá,
todo en el inicio, cuando mencionabas pues, los primeros axiomas de la lógica del
sí,
conocimiento. Pues Andrés
ajá,
dijo algo que pues, me pareció interesante y es que hay gente que no sabe lo que ignora, ¿no?
sí,
Eh, entonces,
ese,
pues lo que se me viene a la mente es, bueno, podríamos como transformar esa lógica del conocimiento como una lógica de conocimiento basada en estados de conciencia, tal vez, porque digamos que eso
uy,
correspondería tal vez más como en la práctica. Y, o sea, el inicio fue como una sola idea, pero pues cuando ya hablas de lo de la dinámica, pues cobra
ok,
más sentido, porque puedes, digamos, pasar de
nunca
un
es,
estado de conciencia a otro dinámicamente, ¿sí?
sí, nunca he pensado en eso, como nunca he visto que traten esas ideas, pero oiga, es muy interesante, nunca se me había ocurrido, y no he visto como ningún trabajo por ese lado, ni idea, no tengo ni idea, pero
Sí.
sí, claro, oh, sí, digo, es que creo que sí, tal vez lo he pensado inconscientemente, pero
En otro estado de
sí,
conciencia.
en otro estado de conciencia, probablemente así medio dormida, así, después, bueno, en ese momento cuando nos ha tomado como 3 tintos antes del mediodía, comienza a dudar de todo su conocimiento, y me dice, ¿esto fue una mala idea? Sí, es una gran pregunta. No, nunca he escuchado de algún trabajo parecido. Sí. No, y el axioma 5 justamente es parcial, es como polémico porque no siempre uno sabe lo que ignora.
Sí,
Hay cosas que uno puede decir, no, yo no sé eso, y claro, pues uno tiene que ser consciente de que no sabe sobre algo, pero sí,
Pues
en
uno
muchos
tiene que
casos
ser
no
consciente que no
aplica.
lo puede deducir a partir de su conocimiento.
Exacto.
exacto.
Y
Esa
esa es la
sería
parte
la...
difícil.
Ajá.
Ujú.
Y también yo creo que se involucra mucho en los axiomas de las creencias, sobre todo en el último axioma que mencionabas, que tienes como tus pensamientos, en el que dice que, a ver, ese axioma decía que cuando uno cree en algo, uno cree que ese algo es conocimiento, ¿cierto?
Sí.
Ujú.
De alguna manera es
¿Me
como,
pasé?
pues,
Me pasé.
sí,
Sí, te pasaste.
sí, te pasa.
Ahí está.
Acá. El
Es
último.
strong belief, sí.
Sí.
Pues de alguna manera es como la eso sí podría ser como ya más amplio, pero es como la conciencia del término propio fi, o sea, de qué es fi en realidad, ¿sí? O sea, porque
Ajá.
uno puede creer en algo, pero no entender bien cómo cree en ese algo, ¿sí?
¿Cómo creen ese algo? Sí.
Entonces, bueno,
Sí.
yo creo que ahí está como muy interesante y además que es como una, o sea, claro, la manera en la que se da la dinámica, pues que mencionaste, así como que alguien dice algo, entonces yo tengo nueva información y sí, es muy interesante, pero me parece que también puede funcionar mucho pues con el propio estado de conciencia de que voy descubriendo las cosas. Eso inicialmente podría pensarse que funciona pues más para entender tal vez cómo piensan las personas o cómo sí, desarrollan la información o cómo la reciben, lo que sea. Pero también en
Sí.
cierta forma se puede entender como, como una máquina, ¿sí? Que va leyendo información, pero digamos que en la práctica tiene cierto tiempo para leer una información y cuando no la ha leído toda, pues digamos que está en un estado de conciencia, ¿sí?
Ujú.
Ujú.
Sí, eso, o sea, literalmente eso aplica directa a los jugadores de ajedrez. Cuando tú
Mm,
sabes, digamos, ves la información en tablero, puedes medir cierta cantidad de jugadas y crees que tal jugada es la mejor, simplemente porque de pronto lo que te faltó fue más tiempo de análisis para saber cuál jugada era mejor.
claro, por
Y ya.
ejemplo, una máquina, digamos, si uno está jugando en una aplicación y eso, a uno
Ujú.
la máquina le dice la mejor jugada es esta, ¿no? Y uno deja que la máquina siga procesando y le dice, no, la mejor jugada no es esa, sino otra.
Sí,
Sí, es
no.
como,
Sí, va cambiando,
ajá,
según.
Sí.
Hay, hay un librito chiquito, menos de como 60 páginas, que toda esta discusión de la pregunta de Sergio y la respuesta de Laura sí, me recordaron, es de Florensky, que él estudió matemáticas en Rusia hace como 120 años, luego siguió haciendo muchas cosas, era muy amigo pues, de Alexandrov y de todos esos topólogos, pero
Ujú.
después se convirtió más en un filósofo un poco místico al final, y después terminaron los estalinistas procesándolo y matándolo, pero tiene un librito que se llama el infinito en el conocimiento, en que la pregunta de partida es lo que, o sea, como que si creemos lo que sabemos, si sabemos lo que sabemos,
Ujú.
y, y parte, digamos, de un núcleo, pero es un núcleo muy filosófico, y luego lo expande a un núcleo que se va a ordinales, de hecho, para ese tipo de respuesta. Lo que pasa es que el libro está en ruso y fue traducido al italiano y creo que al francés solamente lo he visto en esos idiomas, no lo he visto ni en inglés, ni siquiera, y mucho menos en español, no sé si está por ahí. Pero el punto de partida es exactamente esta, como lo que se está discutiendo en este momento, y es una pequeña joya, ese libro, de Pavel Florensky.
Bueno,
Sí, estaba mirando aquí el libro de Hintika. Es un libro chiquitico, chiquitico también, pero justamente tiene toda esta discusión de cuáles axiomas uno debe admitir y cuáles no, y ahí no está, estrictamente no está escrito este strong belief axiom. Sí, hay otros parecidos, pero no. No, yo sé que ese strong belief axiom lo introdujo fue Stolnaker y sinceramente no leí cuál es el argumento para admitirlo. O sea, no lo tengo muy claro. Porque en algún momento lo traté de leer y no me convenció y nunca jamás lo volví a leer con detalle. Sí. Por ejemplo, justamente el axioma 5, el de la introspección negativa para el conocimiento, que uno sabe lo que no sabe. Sí, en yo también al comienzo, uno entra como con escepticismo, pero ya uno lee como los argumentos que da gente que ahí dice, bueno, listo, yo ahora sí le creo un poquito más de que uno puede aceptarlo, asumiendo que pues está tratando de simbolizar, de reflejar pues cómo piensa una persona bastante inteligente. Sí, pero sí, uno no sabe lo que ignora. La mayoría de la gente creo que le aplica esa frase, de que uno realmente no sabe lo que ignora. Sí, Pi.
ok.
Bueno,
Bueno, pues yo me tengo que ir, pero muchas
gracias.
gracias, Laura, por tu charla.
Listo.
Estuvo muy,
Bueno, yo también ya.
muy buena. Para mí que no sabía nada de lógica modal, estuvo bastante informativa.
Sí. Ok.
Sí,
Entonces.
pero chao a
Bueno,
todos.
chao.
Cuídate.
Oh, gracias.